And one thing I should say is that I'm pretty sure the online homework will force you to round according to the rules of that we're going to talk about here. You haven't had to do any put numbers in yet, maybe. But significant figures. For sure, when it comes time for me to assess you at the end of a unit with a unit exam, I will be looking for you to round according to the rules that we're talking about. And we're going to talk about the different rules for adding and subtracting versus multiplying and dividing. That's what's coming up next. So, for instance, if you have, my unit exams always have the problems at the back. I will tell you, a lot of times my unit exams, and I will probably keep the same pattern, a lot of times the front of my unit exam asks for like vocab words, so don't blow those off. You might want to make note cards to get ready for the unit exam. So say you have a problem at the end of the test and it's, it takes you maybe 5, 6, 7 minutes to do the problem on the exam. If you don't round right, you're gonna lose 1 point. So maybe it's worth 5 points and you lose 1 of those points. Okay. So this is all kind of a big, hairy deal. We were talking about the number 32,000, and you guys told me that the decimal is really there, but it's what I say implied, so I'll put a little dot around it. If there is no decimal there, if it's just implied, then the convention is that I've only got 2 sig figs. But if I want to make any of these zeros significant, my best bet is to pack it up in scientific notation and show those as trailing zeros after the decimal. Okay, seems kind of strange, but that is true. I swear, when I was taking this years ago, and I haven't seen it since, so I hesitate to say it, but I thought you could, if you wanted to remove the ambiguity, you could actually put a line over the 0 where the uncertainty begins. I don't know, I haven't seen that convention. Maybe it was just my quirky chemistry professor. But, okay, so we talked about significant figures. Significant digits means the same thing. Now we need to talk about how you're going to, throughout this course, round your calculated numbers. Okay, remember that all measured quantities have uncertainty in the rightmost digit. Some measured quantities, the quantity that's exact, there are 2 types of exact measured quantities. That would be by definition or by counting. So no uncertainty in those. So you have to keep that in mind too. We're going to start with adding and subtracting. So my pen. So if I add / subtract, okay, so that's the 2 operations here. We're always going to be fewest. In this case, it's decimal places. Okay, we actually do less adding and subtracting in this course. What we do more of is multiplying and dividing. So what you're going to do is you're going to take your calculator, you're going to add, subtract, subtract, whatever. You're going to calculate, it's going to spit out a number, and then you have to round your answer to the fewest decimal places you had in all the terms you added and subtracted together. Okay. And I'll try to kind of show you why that is. So let's say you're using 2 pieces of glassware and you have a different degree of uncertainty in them with regard to how precisely you can measure volume. Let's say you had an expensive piece of glassware and you knew it to the nearest, let's see, this tenths, hundredths, 1,000ths place. And in the other case, you only knew it to the nearest tenths place. Well, you line them up. And remember the other day we talked about the red number? So the red number is uncertain. Now, when we add those 2 volumes, thou shalt have only 1 uncertain number. So here we go. There's the first volume. There's the second volume. So what we know to do is add them, line them up, add them up. Okay. So my 2 is red hot in the 1,000ths place. And my 6 is red hot because it came from the red hot 4 and the normal 2. Okay, then everything between them is uncertain as well. So thou shalt only have 1 uncertain digit. So I have to truncate it here between the 6 and the 4. okay? So truncating here between the 6 and the 4, and since the 4 is less than 5, I'm going to go ahead and leave the 6 the way it is. If that number had been 5 or greater, I would have had to round the digit up when I was truncating. Okay, it's probably kind of like as you learned it before. But can you see where, just simply put, I'm adding two numbers. Okay, my calculator spits this out. I look at the two numbers I added, and I have to point to the fewest decimals. I have 1 decimal here, and I have 3 decimals there. So I can only go with 1, I can't go with 3. And that's exactly what we reported. So I kind of showed you a long way why it is. Now, we say uncertainty propagated through the little math problem. So this one is multiplying and dividing, okay? And we're conservative, but we're going to count sig figs. So it has a similar feel where you're going to put all the stuff in your calculator and you're going to multiply and divide just your little hearts out. And then whatever your calculator spits back, you take one last look at what you multiplied and divided, you count sig figs, and whatever's the fewest, that's what you round your answer to. And I'll kind of try to show you, try to convince you why that works like that. So if we wanted to get area of something that was a rectangle, we'd take length times width. And so we're going to kind of simply do that. Notice we found the 2 dimensions, and we have different uncertainty in them. We have different, more to the point, we have different numbers of sig figs. I have 1 dimension, 12.34 centimeters. I have 1 dimension, 1.1 centimeter. I'm going to multiply those 2 together. But how many sig figs? Oh, now this is where, see, I don't even have to like have cards or anything. You can hold up your fingers. So how many sig figs in this number 12.34? I'm seeing 4. 12.34, 4 sig figs. Yep, we're counting sig figs, not decimals. How many sig figs in 1.1? 2. So I'll show you how the uncertainty kind of propagates through it. But whatever your calculator spits back, I know it sounds like you're losing information, but you're not. You're being honest to the numbers you multiply together. You can only keep 2 sig figs, and we're going to go from left to right, keeping the first one, the leftmost, and then the second leftmost. Truncate it. Okay, so we know we're going to multiply those 2 together. So the red hot numbers look like this. They're the farthest rightmost digit in both cases. Long multiplication, which I don't know if they show kids this anymore, but we would take this one right here, this red hot 0.1 here, and we multiply it by the top stuff, and they're all red hot. Why? Because that 0.1 is red hot. Okay, and then we slide it over 1, and then we take that blue one and we multiply it by the 1, 2, 3, 4, and 4 is red hot. Then it looks like this. And this is a long multiplication, right? And then we go ahead and we bring it all down, and then, I don't know so then we have like 3 decimal places up there. We have to move the decimal 3 from the right to the left. So if we add these numbers, notice that the only digit that's not red hot, not contaminated, is the first digit. Okay, this one is red hot because this is red hot, and these are all red hot. So you can only keep 1 uncertain digit. So what I said, even before we started this, was you guys told me 2 was the fewest. And so that's consistent with what we're going to do. Now we're going to truncate it here, but in this case, can you see, since we have a 5 here, what are we going to? We're going to keep the 3 or make it round it up? Move it up. Yep. So the answer we would report is 14. More specifically, you'll hear me say no naked numbers. So we can't just put 14. We have to put the units, 14 centimeters squared. The reason we got centimeters squared was when we were multiplying the numbers, we don't only multiply the numbers, we also multiply the units. And centimeters times centimeters is centimeters raised to the 2nd power. Okay. All right. Very good. So this slide just kind of summarizes what we did on the last few slides. I kind of tease, this is one to put on your refrigerator. Again, we do a lot more multiplying and dividing than we do adding and subtracting. Tomorrow you'll be collecting some data and doing some relatively simple calculations. First off, when you collect the data, make sure you and I'll try to cover this in pre-lab, make sure you get the data to the right number of digits. Okay. The other day we looked at using a graduated cylinder and estimating between the divisions. Okay. So your lab format will already kind of pull that out of you. Feel free, if you're trying to kind of get a head start on labs, is to take your lab notebook and you actually can go ahead and I just say format it. So you can put the title of the lab, and at the end of the lab write-up, the experiment that you're going to do, it tells you the format. You can already kind of put those blanks in there. Or you can do it as you go. All right, so like I said before, there's two types of exact numbers. There's one by counting. I can count the number of heads in here. It's not plus or minus one person. It's like I know that's how many people there are. Okay. The other one is by definition. If you are using, for instance, we know that, let's see, 1 meter in terms of centimeters, 1 meter is equal to how many centimeters? We did this the other day. 100. Yep, 100. Now that's an exact relationship. There's no approximation there. And so if you're using that relationship to work a problem, you don't count sig figs and round according to those. Okay, the other one I told you the other day, 1 inch is equal to how many centimeters? 1. Yep. And that is exact. Okay, so there are, within the metric system, all exact, and there are also some exact, some other exact. We don't use those to round, to drive how we round our answer. Kind of think of them as having an infinite number of figures. All right, on to part 4. Dun dun dun. I'm glad we're getting this far because actually this will make tomorrow's pre-lab a little easier, and just tomorrow in general a little bit easier, because you will be measuring the density of stopper and a wooden block tomorrow. So, density. When I think of density, and maybe you guys do too, I think of like how crammed something is or how fluffy something is. Pillows have low densities. Snicker bars have high densities, okay? So what I'm doing when I do that is I am kind of thinking of, if I take a certain volume, will it be very heavy? For instance, if I scale, think of your pillow, your favorite pillow at home, I got kind of a nice one, I think, and go ahead and take, that's a certain volume. What if I were to go ahead, instead of it be a pillow, make it a Snicker bar? Would it weigh more? I think so. Okay. To calculate the density of a Snicker bar or a pillow, all we got to do is get a fix on its mass, get a fix on its volume, and then do one little division problem. Now, sometimes I run into students wanting to use the letter D for density. No, we're not doing that. We're going to use Greek letters here and there, and this is one of those cases we're going to use the Greek letter rho for density. All right. So if density is a ratio of mass to volume, sometimes density can be kind of a moving target with regard to temperature. So density, I got a whole bunch of new markers, and is mass divided by volume. So if I change the temperature of something, the mass isn't going to change, but the volume might change a little bit. You guys have seen this before, I know. On a cold day, you have a bottle of water that you've been drinking in your car. You might go in after, if your car cools down, and you might see that your water bottle is collapsed. Basically what's happened is you had the lid screwed on good. Well, even if you didn't have the lid screwed on good, there's an amount of air in your bottle, and at the lower temperature, those gas particles, the air, they go slower at colder temperatures. And the same number of gas particles occupy a smaller volume. Okay. So in general, what I just described, and it kind of makes sense if you think of all matter as moving, if you slow it down, the matter moves more slowly. So in general, as you cool something down, let's see, I'll do this. Okay, temperature. Okay, we're cooling it down. As you cool something down, in general, the volume should go down. Just based upon what we call the kinetic molecular theory of matter. All matter has motion. Okay, we're slowing down the motion. This, by the way, is, speaking of solids, why when they're building, they're pouring concrete sidewalk, they always segment it. So it can swell in the summertime and contract in the wintertime. So as it turns out, solids are less likely to swell under heat and contract under cold. Liquids swell under heat and contract under cold even more. Gases do it the most. So when we're trying to get to the density of something, I'm going to try to convince you here in a minute, is it does depend upon temperature. The temperature needs to be given. A really common temperature in science is 20 degrees Celsius, which is just a little bit on the cool side. Right now, I'm guessing this room is 22 or so. But the Celsius scale, how do I say this? When you jump 1 degree on the Celsius scale, it's more than 1 degree on the Fahrenheit scale. So you wonder about those folks in Europe where they have the degrees Celsius. I think they should go fractions of a degree almost, because our Fahrenheits are smaller.
They do sometimes, and a half like today. If you went 2.5, they would go.
Okay, they do sometimes, it seems like. But 22, just a halvesies would get it, I think.
Yeah.
Similar to the Fahrenheit temperature. Okay. So, here we have, we're kind of trying to show you the effect of changing temperature and the density, okay? So all that's been done here is kind of take a nice, pretty piece of glass, put water in it, kind of drip some blue food coloring, and then in 1/4 put ice cube, okay? So now what happens around the vicinity of the ice, what happens to the density, what happens to the, well, I'll just answer my own question. The water cools down, and as it cools down, okay, the volume gets smaller, okay, and as this gets smaller, the density increases. So the cold water becomes more dense, basically. So I mentioned that if you're talking about volume and density, but if you're talking about volume, you need to make sure we're all on the same page with regard to temperature. So the glassware that we use in the lab will, if it's a piece of glassware that measures volume very precisely, it will say at what temperature it was calibrated. So anybody remember the piece of, what the name of this piece of glassware is? It's letter V. It ends with flask, but it's a volumetric flask. This is a volumetric flask, affectionately called a vol flask, and it's got one mark, one calibration mark. And this TC stands for to contain. In this case, 1,000 milliliters, and it would give like a, probably like, I don't know if it gives a tolerance somewhere on it, but, and it was calibrated 20 degrees Celsius. This is a pipette. You guys will be using these. I'm pretty sure, do you use these? No, I think you use the other ones. This is a graduated pipette, and in tomorrow's lab, you'll be using a normal pipette. And but my point here is it gives a temperature at which those lines were calibrated. Because if you go warmer or colder than 20 degrees Celsius, the volume may not be what you think you're dispensing. Okay. We talked about properties, and we talked about physical and chemical properties. We know it's a physical property if you can measure it without destroying the sample, basically. It's a physical property if there's no new substances are formed because of a chemical reaction. Clearly, if I just, this is a non-destructive test, okay? Mass and volume, divide it out, give me density. We talked about intensive and extensive. Remember I told you I like to think of intensive as independent of amount, and extensive does depend on amount. So this is an intensive property, not an extensive. So intensive, it doesn't depend upon amount. So this is to say I could have a cup of water, and we're going to see actually coming up the density of water at, I think we're going with 4 degrees Celsius, is 1.00 grams per milliliter. And you will want to memorize that. But if I have a cup of water, the density is 1.00 grams per milliliter. If I have a bathtub of water, the density is 1.00 grams per milliliter. It's independent of amount. That's small amount or large amount. Okay? So units, as you might imagine in science, have to follow how you got that property. So how we got density was we divided mass by volume. Really solid units of mass, probably the most common units of mass, would be grams. Very common unit of volume would be milliliters or centimeters cubed. And I think the other day I told you another thing to memorize. It's nice to have a marker that works. Is you need to memorize that 1 milliliter is exactly equal to 1 centimeter cubed. But anyway, so if these are our units, we need to make sure that they carry through, and so that's why the answer to a density calculation would be grams per milliliter or grams per cubic centimeter. Now, I'm going to, when you see me work problems using density as, I'm going to kind of tee it up here, probably, bless you, on Friday maybe, we're going to use density as conversion factor, and I like to unpack that, okay? So, for instance, when I wrote the density of water is 1.00 grams per milliliter, when I unpack it to use it, I will say the density of water is 1.00 grams per 1 milliliter. I don't know, we kind of catch the subtle difference. This is great to type it out. This is great to work problems. Okay? Sometimes it's helpful to do it this way. Anything raised to the negative power is automatically in the denominator. So here we have grams times milliliters to the negative first. Puts milliliters in the denominator. Grams times centimeters cubed raised to the negative first. That puts the centimeter cubed in the denominator. So just kind of throwing that out there. You might see that in there. So I have some, actually, I don't know what your slides say, but the title of this table should be densities of common materials, not substances. The biggest thing that remember what a substance is? Substance and pure substance are synonyms. So a substance is either an element or a compound. So which one up here is not an element or a compound?
Would be the wood.
It would be the wood. Wood is not an element or a compound. So what do you think? It's not an element or a compound, so it must be a, starts letter M, it must be a mixture. Now, wood. Think of, yes, this is wood. I'm just looking at this wood that makes up these tables. How many people think, I'm going to homogeneous or heterogeneous? How many people think that's a homogeneous mixture? How many people think that's a heterogeneous mixture? So why is it a heterogeneous mixture?
It's got it's not all the same.
Because the color.
Solid, it's not.
Yeah, it's not all the same. And I am not a biology person, but I like to dream. I just think that's neat how the characteristics of the carbon and the hydrogen and oxygen that make up the cellular material that make the wood. So I can tell it's heterogeneous because I have different kind of colors. And that must mean on the molecular level that something else, difference going on there to give those colors. Okay. Okay. So this one is increasing density. This one's kind of a little bit all over the place. Here's the first column's solids, the second column's liquids. Why do you think gasoline has got a range like that? I think a couple of reasons. Different grades of gasoline, maybe? Yeah, different grades, or Sometimes it's just a wildcat to measure, so it's liquid state. And then we have some gases here. What's the difference between the units for the gases versus solids and liquids?
Liters.
Yeah, exactly. Yep, it's per liters instead of milliliters. Does that make sense? Kind of to get a mass you can sink your teeth into, you've got to get a larger volume. Milliliter is about, well, kind of like the tip of your thumb. And a liter is about a quart. No, yeah, about a quart. Okay, very good. So in order to find the density of something, you guys are going to be doing tomorrow, you're going to use the scales to knock out the masses of the two objects you're getting the density of. And then we're going to get to the volume a couple different ways. And I'm going to go actually through both of those ways here. Now, this last one I take a little bit of exception to. It says, go ahead and get the mass and volume. This is take the ratio. Ratio just means division. Do a division, that's a ratio. And then the last one says make sure that your units are either grams per milliliter or grams per cubic centimeter. Well, that violates what's the densities of gases? Usually grams per liter. So I don't know. So let's do an example. Tomorrow you guys are going to have a wooden block. And in this case, it's not wood, it's some sort of metal alloy. And we have the length and the width and the height, the three unique dimensions of that block. So how can we get volume?
Length times width times height.
Length times width times height, exactly. You got it. And notice they went ahead and weighed it for us. 13.94 grams, that's nice. Okay, so we're going to have to knock out the volume, and then once we have the volume, we're just going to take the mass divided by the volume. Nope, I don't think so. Maybe. All right. So, you're probably already kind of familiar with this, but what I like to do if I'm going to multiply a series of numbers together, I just put those numbers in parentheses. So is this where you guys have to fill in the little blanks? Okay, so parentheses means multiply through. So why do we do that? This is where, like throughout the class, if you want to bring your calculator and tap it in, I think sometimes students find that helpful. Therapeutic of sorts, keeps you awake. Okay. Before I show you the answer that I get on my slides, I'll get your fingers ready. How many sig figs in 2.21?
3.
Those are your fingers. Very good. 3. How many sig figs in 1.05?
3.
There are 3. How many sig figs in 0.76? 2. Very good. So when we round our answer, how many sig figs are we allowed? Just 2. Exactly. Okay. So this is what I get. I jotted down my office because I'm also proving a point here. So the long answer you got, the unrounded answer, looked like 1.76358. I got 1.76358, and of course units are centimeters cubed. Now, the reason I would want to round this is because you guys told me 2 sig figs, and in rounding it at this point, then I keep up with what my volume should be rounded to. So the reason I got 1.8 is I kept 2 sig figs. I'm going to round it here. Since this is a 6, I'm going to round my 7 up to an 8. All right, so we're ready to kind of plug and chug. We don't have a lot of plug and chug here in chemistry, but density is mass divided by volume. So all we got to do is take the mass that was given on the previous slide, that 13.94 grams, and divide it by the volume there. Okay. So if I take that 13.94 grams and divide it by 1.76358 centimeters cubed. Now I'm trying to make a point here. On the board over here, I went ahead and wrote the mass, and instead of dividing it by that 1.8 centimeters cubed, I divided it by the unrounded number. If you go ahead and round this out, or finish this thought, you should get something like 7.74 repeating. Okay. So how many sig figs do we round it to? Fingers, yep, 2. Very good. So I'm going to truncate it here. And since this is a 4, I'm going to leave the 7 a 7. So my answer, I would report 7.7 grams per centimeter cubed. Okay? But the reason my slides don't say that is because to get the 7.9, I did it this way. So if you do it, the mass, which again is 13.94 grams, divided by your unrounded volume, you get, I get 7.904376325, of course, grams per centimeter cubed. 2 sig figs, I truncate it right here. Since this is a 0, I leave the 9. Okay, now sometimes students will ask, oh, Mrs. Snipes, you're setting me up. I don't mean to. Either answer is fine. Either answer is fine. Yes, ma'am.
Okay, I cut that into my calculator and I got 7.74 repeating.
This one?
Yeah. So why would that be 7.8 instead of 7.9?
So there's 2 things. I hope this, okay. So to get this one, I took the 13.84 grams divided by 1.8 centimeters cubed. Okay, and that's what you did. To get the one that I reported, I did this.
Okay.
And the difference between the two are what I use the unrounded volume there and I use the rounded volume there. I catch you on the other side if it helps any.
I'm just
Either
kind
one
of
of
confused because
you.
you put that one up instead of the 7.8.
Yeah, I'm just kind of making a point. Either one of the answers. Either one of the answers is great. Yeah. Either one's great. Bless you. Honestly, this one, the 7.9, just I think would be a little bit better because you're using an unrounded number. The advantage of doing this one and writing down your answer 7.7 grams per cubic centimeter, that advantage there is that you have been careful and you know that you only have 2 sig figs. Over here, you've lost that you have 2 sig figs. You just got to remember that I'm limited because of, I'm limited just because of that 0.76. Okay, so, all right. So this talks about no naked numbers. Whenever you write down a number, I'll be walking around tomorrow, being a hard butt. Make sure that you write down your measured quantity or your calculated quantity, and you always have a unit at the end. In science, including chemistry, knowing what units you have to play around with your data and your formulas, can give you confidence that you have the right answer. If the units cancel and give you what you think you should have. Okay, so I want to spend just a minute talking about water. A little bit ago, we saw, we looked at kind of the density of a couple of objects, and here was an ice, okay, floating. So this is what solid water, and this is, of course, is liquid water. Water is unique in that as it approaches its transition from a liquid to a solid, it basically fluffs out. Okay, so if it fluffs out, it gets larger volume, getting ready to crystallize. Okay, if it increases its volume, we're dividing by a larger number, so actually its density goes down. Something that has a lower density will float, and that's why ice floats. Okay. So this figure kind of sums that up a little bit. So if you bear with me, kind of get your orientations, what I want to think of is cooling down. So what we have is temperature along the x-axis, so we're going to get colder, 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 colder. And I'm showing the physical phase of liquid water, okay? So notice that as I go from 10 Celsius, which is still pretty cool, I'm approaching the transition temperature of water, and the Celsius scale would be 0. I'm approaching the transition temperature, but it's still staying liquid. So can you see as I cool down, I cool down, I cool down, those cute little water molecules, they start moving less and less and less. So their volume decreases, so their density increases. It has what we call an inverse relationship. Volume decrease, density increase. Well, this should be about 4 degrees. It has its maximum density. Okay. Maximum density, I told you to kind of commit to memory. The density of water at 4 degrees, and for all intents and purposes, the density of water we need to work with is 1.00 grams per milliliter. Before I go much further, notice that how sensitive the y-axis is. So the y-axis is our densities. I mean, that's like gnat's eyebrow, sort of. Well, what happens as water cools and transitions from a liquid to a solid, okay, is it fluffs out. So check this out. Check out that jump. So when it goes from being a liquid to being a solid, it occupies more volume. Increase the volume, decrease the density. So that's why it does that. Isn't that crazy? It fluffs out. But now notice as we have water in its solid state and we cool it down, what happens to the density? As you cool ice. Does it go up or down? It goes up. The density goes up. So this, my friends, is why you don't put Coke in the freezer to cool it down. Because if it changes phases on you, then it's going to actually occupy a larger volume than it otherwise was. This is kind of showing you the same information. Here's one for you, just kind of giving you, these are similar volumes, okay? This could be your pillow, this could be your Snicker bar, similar volumes. Which one is more dense, do you think? The styrofoam or the rock?
The rock.
The rock's more dense. So if we let the rock and the styrofoam interact with water, this is what happens. So would you say you would say that the density of the water is between that of the rock and the styrofoam. That's what I would say. Okay, well that brings us, we should try this. We got a few minutes. Okay. We're gonna do this example. It's gonna help us tomorrow. So let's run through this example. So notice that we are going to come up with the density of something. Actually, no. Oh, that's fine. I'll just do pre-lab on something like this tomorrow because it looks like we're all one to go. So that'll work. We'll start there on Friday, and then tomorrow we'll do pre-lab. That will be wonderful.
Yeah, because I found it's okay, that's what I found.
Yep. So for the regular lab.
Yeah, the regular lab should help increase, so we'll go to experiment 1 and have any answers.
Also, if we don't get all of them right, like we do what we think it is, we're gonna.
Okay, yeah, that's right, Craig.
Okay.
Definitely, because what doesn't work is if you come in and there's nothing.
There's nothing in that?
Yeah, but it's blanks. Yeah, but it's blanks.
So it's better to put down something.
Right.
Okay.
But if you just put down la la la,
I guess you
well,
just
let's see what the answer is.
Yeah, exactly. Did you actually look for it yet?
Yeah. So, You got a minute? Yay.
Have you gotten one for It's so expensive. It's like $175.75. That's
Single
used.
Friday.
That's used. How much is it worth? Do you need it?
He says we're gonna work out of it, but.
And I don't want to miss the opportunity to give it to him and realize you do need it. That's a lot for a partner.
Yeah, you show up, I think, pretty much.
All the photos are online.
Yeah. Look it up.
Yeah, copy the question.
One of
put it in
my, like,
Google.
my intro to ethics class, all the answers I found out, all my tests, no, Quizlet.
Yeah.
Okay, you think I'm really gonna read that book? Did that microeconomics and the appreciation. I passed. Oh, yeah,
So I figured out my phone. So I didn't get it done when it was late, sadly. But I did get it finished, it just says it's late. Will you check and make sure I got the ones due today done?
Okay, so you have chapter 2 done?
I think, but can you make sure I
I
got it
can,
done?
do you wanna wait?
I have time, my class is done.
Okay, cool.
Because like I seen you grade it and I said, why does it say that I don't have a, and then I realized apparently I didn't do it, I didn't catch it.
Well, I don't think in the big scheme of things that's going to be a
Big problem,
no.